Hello dear learners. In today's lecture, we will continue our discussion on Sun and interplanetary space. Last lecture, we have learned about various important or vital statistics about the Sun, its mass, its uh, gravity, its escape velocity, and more importantly, how the energy is generated at the core and how this energy makes it radially outwards and makes the photosphere at an equilibrium temperature of 6000 Kelvin, how the temperature inside the sun varies, etc. So, in today's class, we will continue with what we have learned in the last lecture. So, if you take a close-up image of the photosphere, this is how the sun looks like. So, photosphere, for all practical purposes, the notation is photosphere is the yellow disk that you see in the sky. Okay, this is how it looks like. Okay, and you see these small granules are basically each of these granule, which is very, very large in comparison to the size of the Earth. Each of these granule is actually a convection zone, and the dark boundaries are the places where the matter is downwelling. And you see, if you zoom enough, if you even zoom into this picture with an actual instruments, you will be able to see the convection pattern or the upwelling of mass from the interior of the sun, bringing out the energy. Right now, in today's class, we will look at each of these layers. We have talked about the interior in the last lecture. Interior, as in the core, radiation zone, convection zone. In this lecture, we will try to understand basic aspects, very basic concepts about the exterior of the sun, the surface and the atmosphere of the sun. The photosphere is the origin of the 5800 Kelvin black body radiation that we see. So, we've done that simple calculation, right? Depending on the temperature, where do you expect maximum amount of energy to be concentrated? So, for that, the temperature that you're going to use for sun for all practical purposes is approximately 5800 Kelvin. Okay. So, at the photosphere, the density is so low that the gas is again transparent to light. Why am I talking about transparency? Because in the radiation zone, the entire radiation zone is transparent to light because all the atoms are completely ionized. So, energy or electromagnetic radiation cannot be absorbed by any species, I mean any chemical element that is present there, right? So, here because of the density being low, the region is again transparent to light. Okay, so the hot convection cell tops radiate energy as a function of their temperature, which happens to be 5800 Kelvin, right? So, that's what I was talking in the beginning. So, if you use this temperature in the lambda T is equals to constant equation, you will realize that the lambda max, Wien's displacement law, lambda max would be 480 nanometers, which is pretty much in the visible range. So, lambda max times T is equals to constant, which means lambda max is inversely proportional to the temperature. So, larger temperatures, black bodies with larger temperatures will be radiating in the smaller wavelengths, and black bodies with very low temperature, cooler temperatures will be radiating in the infrared wavelengths. That is the meaning of this. Okay, and photosphere is responsible for the light that we see, and that's why we see this as a surface, right? All right. So, the plasma that is coming out from the photosphere, or they originate from what we call as the sunspots. So, photosphere is also home to these features, sunspots and granules. Granules we already know. Granules are the convection cells, basically, right? So, sunspots. What are sunspots? Sunspots are also appear on the visible disk. If you go back to this previous image, these dark patches that you see on the sun on the visible disk, if you have a sensible instrument, you can see these spots with your naked eye. Okay, so these features are called as sunspots. They appear dark, and what are those? They are formed by the concentration of large magnetic fields greater than 1000 Gauss and they appear dark because their temperature is cooler, or the temperature is lesser in comparison to the ambient temperature. So, the ambient temperature you put at a reference of 5800 Kelvin, then the temperature of the black spots that you see on the sun will be of the order of 4300 Kelvin. Okay. And granulation is a small scale pattern of convection cells, and which results from the temperature gradients close to the surface. Why I am calling it as temperature gradients close to the surface, this again goes back to the fundamental idea where the size of the convection cell is becoming increasingly smaller as you move towards the surface, right? So, that is the basic meaning of this. All right. So, if you look at the atmosphere, everything above the photosphere can be considered as the atmosphere of the sun. So, atmospheric composition is hydrogen, helium, oxygen, and so many other species. So, hydrogen seems to be the most dominant species in the atmosphere, with percentage of total number of atoms or total mass of hydrogen in the atmosphere will be of the order of 71%, and helium is of the order of 27%. And interestingly, this probably is the the composition is not different from what you can see in the interior. And more importantly, this chemical composition, atmospheric chemical composition, is pretty much same as what you can see on Jupiter, okay, or the rest of the universe. Okay. So, before all the heavy elements form, so the basic species are hydrogen and helium. So, immediately sitting above the photosphere is the chromosphere, and chromosphere is a less dense but high temperature gases are existing at this in the chromosphere. So, it was first observed over the edge of the moon during the solar eclipse. So, when solar eclipse happen, the annular disk is completely covered by the moon. It appears as if it is sitting exactly matching exactly in size. So, the distance from the moon to Earth makes it a very rare event wherein it completely covers the visible disk, solar disk, exposing the outermost features of the photosphere or the chromosphere or the corona. Because once you black out the yellow disk, you will be able to see this minor features which are like gas escaping and this plages and these ejections. These are not otherwise visible when you have the full disk in front of you, because it will mask, the full disk will mask all these features, and that's why only during the times of total solar eclipse you will be able to see these features. Some features like spicules, plages, and filaments, etc., can only be seen when solar eclipse happen, and these phenomena are present in the chromosphere. That is important. So, spicules extend upwards from the photosphere into the chromosphere almost, and more importantly, the chromosphere is a very low density uh, very low density region of the sun's atmosphere, but at the same time it's also very hot. That means the temperature is very large. So, energy from the below, that is from the photosphere, excites the atoms and produces various emissions in this layer. Emissions as in energy coming from the photosphere in terms of, let's say, electromagnetic waves, or in terms of particles, excites the atoms and molecules in this chromosphere, and they emit radiation when they are subsequently de-excited. Okay. And the predominant element in the chromosphere is basically hydrogen, that we have already seen. And the most important, the prominent line that you can see is H alpha, which is something like 121.6 nanometers. And why do we call it as chromosphere? Chromosphere basically refers to color. That's why we name it as the chromosphere. Okay. And now moving away from the photosphere, we have to remember the prominences or the filaments that you see on the visible disk. These filaments are these features like you see here. Filaments are these features. These visible prominences are called as plages. Okay, and these are the ejections which are which are intertwined with the circulation, the polar circulation of the sun. Okay, so prominences and filaments are cool volumes of gases suspended above the chromosphere by the magnetic fields. So here you are also introducing the effect of magnetic fields into the movement of this plasma. Plage is a hot plasma relative to the chromosphere, usually located near the sunspots. Right. So these are the sunspots. The sunspots are masked by the visible outburst of the plages. Right. So these are the sunspots. Right. Now, if you talk about the spicules and prominences, they are emissions from the atmosphere is very faint relative to the photosphere. Okay, they are very faint. You won't be able to see them otherwise. And what else constitutes into this? Violent storms in the chromosphere, giant curved prominences, long thin spicules. All these features can be seen in the chromosphere when you mask the visible disk. Okay. So, solar prominences, like I've been mentioning since the beginning, are major or large scale events, just like this coronal mass ejection, which is releasing a lot of plasma into the interplanetary space. So, these two are actual images where you see the coronal mass ejection being thrown out into the space. Okay, and the scale of this ejection seems to be very large in comparison to the size of the Earth or something like that, right? So, for reference, this image picturizes the typical size of an actual image of the solar coronal mass ejection thrown into space and the size of the approximate size of the Earth in comparison to the size or the scale of the coronal mass ejection. Now, most importantly, this image itself manifests the importance of understanding these things so that we can have an idea of what can happen if these coronal mass ejections, extremely energetic coronal mass ejections, if they make it to the Earth, or how do we develop capacity, or how do we equip ourselves with enough scientific knowledge so that we will be able to predict the occurrence or the arrival of these coronal mass ejections into the geospace. So, geospace, basically the proximal space that is surrounding the Earth, like magnetosphere, ionosphere, thermosphere system, right? Right. Now, sun, you can see sun in different wavelengths, and different wavelengths will reveal interesting information about the sun, which is not generally available or generally seen. So, this is an image taken in the H alpha, like 120 nanometers. You take this image, then you will see these features, these bright features. You also see these plages, these sunspots, and just below the sunspots, you also see these plages, etc. Right. Now, moving ahead, so what have we done so far? We have seen the surface, which is called as the photosphere. Then we have seen what is the chromosphere. So, what we have understood is that the features of the chromosphere are prominently visible during the times of solar eclipse. Okay. Right. Now, moving ahead from the chromosphere, you move into what is called as corona. Corona is where the spicules and other magnetic activity carry energy up to the transition zone. Transition zone is something in between. So, 10,000 kilometers above the photosphere, temperature climbs to 1000 Kelvin, okay, or 1 million Kelvin. So, 1 million Kelvin starting from about 10,000 kilometers from the photosphere, where the photosphere is still sitting at 5,800 Kelvin. Okay. So, temperature seems to be rising about 10,000 kilometers. So, yeah, remember the photosphere is only existing at 5,800 Kelvin. So, what does it mean? It means the temperatures are more than the source. So, sun, let's say if it is a heat source, is able to heat the coronal region to a temperature which is larger than the temperature of the source itself, which is pretty much against the thermodynamics. Any object cannot cool any other object above its temperature, right? You cannot, a heat engine cannot heat another object to a larger temperature, right? So here we are talking about a gradient of 5800 Kelvin to 1 million Kelvin. Okay, so this hot, low density gas at this altitude emits the radiation we see as the corona. So corona is basically again visible during the times of solar eclipse, where you see the corona as a gas which is escaping from the sun. Okay, so extension of corona into the interplanetary space is what is called as the solar wind. So solar wind is above the corona. It refers to hot and energetic plasma, which is covering these 2 points. So which is like steam above a boiling pot of water. Okay, if you see a boiling pot of water, you will see that steam is going away from the top. So it is similar to the sun. You consider as a boiling pot of water. So the gas that is escaping from the sun is solar wind in this case. So wind passes out through the coronal holes. We will talk about coronal holes maybe in the next lecture. And so this is basically telling you that that hot plasma is escaping the gravitational pull of the sun. Okay, simple, right? So which means solar wind, as we see, carries away millions of tons of solar mass each second. Every second, it takes away millions of tons of solar mass. So what and all constitutes solar wind? Which particles will come through solar wind, and what are the typical energies, etc. That we will discuss much later. But now it is enough for us to understand that solar wind is a constant stream of particles which are escaping the sun's gravitational pull and extending towards the edges of the solar system. What is solar wind? Solar wind is obviously plasma, highly energetic plasma, and sometimes it will be supersonic in nature. Okay, so which means there is a lot of gas that is going away from the sun. So millions of tons of mass is escaping from the sun each second. So millions of tons or millions of kgs of mass will still be not so much. If you take the sun's mass in the last 4.6 billion years, if you consider the sun's age so far to be 4.6 billion years, only 0.1% of the total mass has escaped via solar wind from the sun. So considering the mass of 10 to the power of 30 kg. Okay, you can do this simple calculation where you consider 1 million tons of mass escaping for every second. Okay, you multiply that number to reach 4.6 billion years, 4.6 billion years into number of days, into number of hours, into number of seconds, multiply with 1 million tons, you will realize that only 0.1% of the total solar mass has been able to escape the sun's gravitational pull over the past 4.6 billion years. Okay, now we are slowly moving away from the sun almost towards the earth. Right now we have seen what is photosphere, what is the chromosphere, transition zone, and the corona. And now the corona has been expanding and moving away from the sun in the form of solar wind. Now this solar wind has now reached the proximity of the earth or the geospace. So solar wind, as it passes through the solar system, may reach some terrestrial planets, and these planets may have some atmosphere, with some major species like oxygen, nitrogen, anything, hydrogen or helium, carbon dioxide. So when this energy is precipitated into this atmosphere, atomic excitations and de-excitations will happen. Subsequent emission of light basically is what you see in the form of aurora. So aurora is a valuable tool because aurora will tell you what could be the chemical composition of a certain planet depending on the light that it is radiating. Okay, so consists of electrons, protons, and other charged particles stripped from the sun's surface. This is the solar wind that we are talking about. So solar wind consists of electrons and protons, and other charged particles as well, which are basically stripped from the surface of the sun. So, this interaction of this solar wind with the planetary magnetic field gives rise to aurora, because planetary magnetic field should allow these particles to penetrate into the atmosphere. Only then the interaction that I was telling about, like excitations and de-excitations, will be allowed. As a result, you will be able to see the aurora. Right. Now, this is a very important puzzle, which tells you how the sun's atmospheric temperature is changing with respect to height. So, let us put to perspective the way temperature changes in the Earth's atmosphere. So, I'll have a rough axis on the x with, let's say, temperature, and on the y I have the geometric height in Kelvin, in kilometers. Okay. So, temperature initially decreases and then increases and then decreases and increases. Okay. This is a zigzag way in which we know that these regions are identified as photosphere, troposphere, stratosphere, mesosphere, and thermosphere. Right. So, we know the reason why the temperature changes the way it does in the case of Earth's atmosphere, and this seems to be very logically easy to accept, that temperature decreases because of certain species in the mesosphere, etc. But why does, if you look at the temperature change with respect to height in the case of sun, it will appear that the photosphere temperature can be 6,000 or 5,800 Kelvin. Starting from that, temperature will initially decrease up to, let's say, 800 or 900 kilometers, and after that, temperature steadily starts increasing as you are moving in the chromosphere, which means for larger displacements of altitude, the change in temperature is actually not much. This is the region, right? So, you see that the increment in the height is almost of the order of thousands of 1,000 kilometers, but the change in temperatures is of the order of few thousands of Kelvin. Okay. And then subsequently, after chromosphere, let's say at these altitudes, within a shorter range of change in altitude, the temperature changes by several orders of magnitude, reaching what we call as 1 million Kelvin by the time it reaches the corona. So, this is what I was mentioning about simple violation of thermodynamics, where the source of energy for this altitude region or any altitude region is obviously the surface of the sun, which is sitting at 5,800 Kelvin. So, which cannot heat anything else, any other object, any gas or any fluid above the temperature 5,800 Kelvin, because we should also accommodate the transmission laws or whatever it is. And as a result, we cannot expect any other object in contact with this object to be heated to a larger temperature. But what you see here is that it is the coronal region is at a temperature of 10 to the power of 6 Kelvin, which is several orders of magnitudes larger than the temperature of the photosphere. So, this is an anomaly, or this is a puzzle, that how you expect the temperature of this corona to be much larger than the photosphere. There are many other important aspects that we have not included in our discussion, which might actually explain why the temperature change, abnormal or abrupt change of temperature, can occur in the corona. Right. So, this is the apparent surface of the sun, which is photosphere, and then we have the visible, these regions which are visible, the chromosphere and the corona, which are visible only during the solar eclipse, like I already told you, right? And the temperature of the corona is immense in comparison to the temperature of the photosphere, right? So, heat flow is in this direction, right? Then, how do we know so much about the atmosphere of the sun? Because if you say the electromagnetic radiation is traveling from the sun towards the earth, if you record a spectrum of this radiation, you will realize that many lines in the continuum are missing. These missing lines represent all those species which are lying in between and are able to absorb the incoming radiation. That's why you see those lines as missing. These lines are called as Fraunhofer lines. So, the spectrum of sun shows thousands of Fraunhofer spectral lines, which indicate the presence of nearly 67 different elements in various stages of excitation and ionization in the lower solar atmosphere. Okay, so the numbers give wavelengths in the nanometer. So there are approximately 67 different elements in the atmosphere of the sun itself, which are able to absorb all these different lines. Okay, so you can see many species which might be present in the sun's atmosphere. Okay, so how do we get the information, the spectral line information? So the photons with energy is well away from the atomic transitions can escape from relatively deep in the photosphere, but those with energy close to the transition are more likely to be reabsorbed before escaping. Okay, that is the basic idea. So energies with photons with energies well away from any transitions can escape because they are not getting absorbed relatively deep in the escape from relatively deep in the photosphere, but those with energies close to a transition are more likely to be reabsorbed before escaping. So the ones we see on the earth tend to come from higher and cooler levels in the solar atmosphere. So the inset in this figure is showing two absorption lines where this energy is already absorbed by the time it reaches the earth. So the inset shows a close-up of tracing of two of the thousands of solar absorption line, the H and K lines of calcium at about 395 nanometers. Right. So these two lines are absorbed. So obviously these two lines should represent a particular region in the solar atmosphere. Moving ahead, we can now discuss about the active sun or the sun's how the solar activity changes over the period of time. Right. So before moving ahead, we'll have a quick recap. So far in our discussions, we have clearly understood some very basic aspects about the sun as a star, and then about the sun's interior, how the energy is generated and how the energy is moving radially outwards, in which way, in which mode of transfer this energy is moving out, and as a result of whatever it is, the photosphere is maintained at a particular temperature. And you talk about photosphere, then you have so many features about photosphere. What is the temperature? What are spicules? What are plages? What are granules? What are solar prominences? All these are, photosphere is home to all these features. So we have basic definition level of understanding about all these features, and then we move away into the atmosphere. Atmosphere consists of all this transition zone, chromosphere, corona, and subsequently the expansion of corona into the interplanetary space is called as the solar wind. All these things, right? Now, some of these regions are visible only during the total solar eclipse. We know why. Then moving ahead, how do we know this information is using basic spectroscopy, and spectroscopic tools will tell you what elements are present in the sun's atmosphere, probably at what temperature they are existing, etc. So in the next or subsequent lectures, we will try to understand the solar activity. The primary question being, does the sun emit same amount of energy at all times or not? This question will be answered in the subsequent lectures.